All right, we're going to get started. So today's Tuesday, Wednesday of the AB cycle. So Tuesday in Canvas, we have this probe, which is a warm-up riding in a car. We're going to take a look at this. I'll give you a couple minutes just to read through it, then we'll have some opinions there. Then we're going to go through some notes on uniform circular motion, the horizontal. So that means instead of up and down like a Ferris wheel or something like this is horizontal, where gravity is perpendicular. So we won't have to worry about gravity today. Next class, different story. And then I'm going to give you some practice problems. I'll get you started on them. There's 11 problems. I'll probably get you started on the first couple. You'll have plenty of time to get it done during class, and I'll keep you in the Zoom meeting while you're completing those practice problems. We're going to start with the writing in the car. This one, I'm going to try to set it to where it fits all on the screen at once. And I think if I put it right there, yeah, we can see it all. All right, so take a second to read through this. We'll talk about it together and go from there. Right, the gist of this is that you've got four students, let's say students or friends riding in a car, and they're going to come up and they're going to make a turn to the right. And let's just imagine they're doing it without coming to a full stop, so they can really feel and be thrown about in a seat of the car. And I'm sure you've been in a car before that kind of takes a curve with a little bit higher speed than normal, and you're kind of thrown to the side. And let's say that they're taking this curve to the right. And you can imagine when you're in a car and you take a curve to the right, you lean against that left door if you're on the left side. And here we've got Ina, Ree, Chris, and Roberto sitting in a car. The car suddenly went around a sharp corner. After the car came out of the turn, they wondered about the forces involved, and this is what they said. Ina said, "Wow, did you feel that force pushing us outward?" So in this case, they're turning to the right, and she's saying a force to the left. "I was pushed against the passenger door." Ree said, "I don't think we were pushed outward. I think we were pushed inward." Let's say to the right, because the curve is to the right. "Otherwise, we wouldn't be turning." Chris said, "I could only feel the force pushing us forward. The force must be in this direction because that is the direction we're moving." Where Roberto said, "Actually, when we started to turn, I think we slowed down a bit. So I think I felt the push backward." So let me stop this share and say, we've all been in a car. We've taken that curve to the right, whether driving or a passenger. And you take that curve to the right a little bit fast, and we all kind of lean to the left. And before we agree or disagree with somebody, what if we had just asked it a different way? Why is it that we lean to the left when we're making a turn to the right? Why is that? Now, audible, so unmic or unmute, mic up and talk to me. Why do we do that?
Because of inertia.
It totally is inertia. It is completely inertia. Your body is wanting to go straight. Your body is wanting to go straight. You're turning to the right. So you're not really falling to the left, you're trying to go in the direction that you were already going. So that's exactly right. Now, if we were to agree with any of those statements, then when we're turning to the right, which direction is the force? Is it straight ahead? The force, not the inertia. Is it straight ahead, or is it behind us because we slowed down? Is it to the left because we feel like we're being thrown out of the car, or is it to the right, the direction that we're turning? What do we think? Which person? I mean, without saying the names, just the direction that each student or each friend chose a different direction. Which one do we want to agree with? Come on, unmic, say something. Let's talk about it.
The right.
To the right. All right, I've got one person saying to the right. Anybody else?
I agree with also.
Okay. Why do we think to the right? What's our thought process?
Well, the car is kind of like pushing us towards the right because
if we want to keep forward and the car is turning, then we would feel the force on our left side because we're like our body still want to go forward when the car is pushing us to the right from the left side.
That's really well stated. I'm glad you spoke up because, you know, we all have our own way of thinking about it or stating it, but that's a really good explanation. You're wanting to go forward. The car is pulling you to the right to make that turn, and you're feeling that as a push on your left side, pushing you to the right. So what we're looking at is when we're making that turn to the right, we're entering a circle. For a short period of time, we're making a curve, a portion of a circle, a semicircle, and we're feeling that force pulling us into the circle. Okay, and that's what we're going to talk about today: is centripetal force, centripetal acceleration, and tangential velocity. So that's really good. So the question was just merely, if we're in a turn, which way do we feel the force pulling us straight ahead, pulling us back, out of the curve, into the curve, and it's into the curve. Let me ask you something else. What would be the source of that force in the car? So that the car itself is able to make that right turn. What is the force that's pulling that car to the right? What force is involved there, we think?
Thrust.
Say again?
Thrust.
Well, thrust motivates us to go forward. Thrust turns those wheels forward. But what force allows that car to curve to the right? Let me ask you a different way. What force, if I removed it, could the car not go to the right? It's a cold day outside. What if there was ice on the ground and you try to make that curve really fast to the right? Could you do it?
Is it friction?
You're missing friction. Yeah. So friction is what allows that. Friction is the force that pulls that car to the right. And we know that because if we put a layer of ice down and try to do that exact same turn, it wouldn't happen. So if you remove friction and you're not able to turn, it must be friction that's allowing you to make that curve. What if you go to Six Flags? You ride the Texas Giant. You go up really tall, you come back down, and those curves kind of bank sideways. So as you're making those bank sideways curves so you can come around, what force do you think is keeping you in the circle there?
Friction. Not friction.
No, because if there was still ice there, I think that those cars would stay on the rails. What else do you thinking?
Gravity. Not gravity. no,
Gravity
so-
pulls down, and this circle is horizontal. So gravity is perpendicular. So I wouldn't want to use gravity on a horizontal circle.
Is
What
it
else?
centripetal force?
Well, all forces that keep you in a circle are centripetal. So what in this case, what force do we think is giving us that centripetal force? I'll wait and see if there's any more guesses, and then I'll tell you what it is.
Normal force.
Normal force, yes. The normal force, by being on that track, and that track is kind of coming up sideways, that track is pushing up and into that circle. So yeah, with the roller coaster, normal force. Well, if I gave you an easy one, okay, I think we can all see like my screen, find my screen and all these screen of people. If I have my keys on a lanyard and I start twirling them sideways, horizontally, what's the force that keeps them in a circle?
Tension?
Tension. Because if I cut my lanyard, cut the string, they would take off, wouldn't they? So tension. So any force that keeps you in that circle, it's going to be your centripetal force. All right, I'm going to switch over, share my screen as a grid, write some notes, draw a picture, give you some formulas so that we can understand all of this, give you the practice problems. That's the direction we're going today. So stick with me as best you can and let me know if there's anything that I missed. Let's see. Okay, so let's see, do the share. Back to this and we'll flip over to the grid. You guys have had a great day so far. It's nice and warm inside the building here, but I think it's freezing cold outside. Fortunately, I haven't had to be outside since about 7:45 this morning when I got here. So all is well. All right, so we've got circular motion. In particular, this is going to be circular motion, horizontal circular motion. So if I just title this circular motion, and I'm going to put horizontal. Next class, we'll do vertical. Now I'm going to talk at the speed that I write, which is not super fast. It will help you keep up and not be overwhelmed if this is difficult material. It's easy material, just be a little annoying. I will try to write most things out so that way if you review the video, you can kind of catch the ideas as you're going along. And if you're taking notes, which I advise because writing things help you learn things, it'll help you keep up as well. And you'll be able to look at the screen and see what I'm talking about. Okay. Now, if we go back just a little bit, we can remember that Newton's second law told us the sum of forces, or net force, same thing, is equal to mass times acceleration. And what we're going to add to that today is centripetal force is equal to mass times centripetal acceleration. Where that little sub C that you're seeing, this little C is equal to centripetal. Centripetal. Okay. Pretty easy so far, right? Formula really hasn't changed. You just threw a C in on the force side, so you throw the C in on the acceleration side, not really challenging you. And today really shouldn't be a challenge. It should be kind of a break to say, okay, I can understand that, and now let me apply it to some practice problems to reinforce it. So that's cool. So let's talk about an object that is moving in a circular path. So my first little bullet point is going to be an object moving in a circular path. An object moving in a circular path is continuously changing direction. Right, that's pretty obvious, but stick with me. Is continuously if I misspelled something, I'm sorry. There's no spell check when you write on the screen. Is continuously changing direction. And therefore, it is accelerating. Now, how do we know it's accelerating? Well, velocity is a vector, right? And as a vector, that means that it is both magnitude and direction. So even if the speed stays the same, even as you go into that curve in your car, you maintain the 20 miles per hour that you entered the curve, and it doesn't change one bit, your direction certainly is changing. You're going from north and you're turning, and now you're going east, still 20 miles an hour. But since the direction changed, that means the velocity changed, because velocity is both magnitude and direction. Any change in velocity is an acceleration, because the definition of acceleration is a change in velocity. So we know that any object going in a circular path is accelerating because the direction is changing. Okay. And then now acceleration can only happen what? When can acceleration happen, or when does acceleration happen? All right, anybody brave enough to tell me? Acceleration can only happen when?
There's a change in velocity.
Oh, yeah, okay. But regarding forces, when do we have an acceleration?
When they're unbalanced.
Yes. We get an acceleration when we have an unbalanced force. So here I'm saying acceleration or accelerating can only happen if an unbalanced force is applied. Can only happen if an unbalanced force is applied. And I kind of stop there because I don't want you to lose the things that you've gotten. I don't want you to lose the aspects of, hey, balanced forces means constant velocity means no acceleration. Well, let's work it backwards then. If I have an acceleration, I don't have balanced forces. All of these things are going to build together. You're going to need to be able to grab information that you've learned in September with a little bit from November and a little bit from March and pull it together and answer a single question. So don't lose those things that you have, build them and make them stronger. And that's just kind of a simple explanation of that. So we know that an unbalanced force is being applied so that we can accelerate an object that's moving in a circular pattern, orbit, or direction, whatever we want to say. Okay. So just a little bit of definitions there. Let's add to that. And let's see, let's put a bullet point here. And I'm just going to write centripetal force. I'll apologize again for my handwriting, but hopefully me talking through it makes you be able to acknowledge or understand what it's trying to say. Here, I'm going to say centripetal force, it's center seeking. And then what does that mean? Center seeking. Well, we said that in the car, when you go on the curve to the right, the force is to the right, is pulling us to the right. That's why we feel that push on our left side. Well, if the curve is to the right, it's pulling us to the right, it's pulling us to the center of that circle. So our centripetal force always points to the center of the circle. And that's why we're calling it center seeking. There's a couple of notes about this. We're going to say that it causes an object to follow a curved path around the center of a circle. Circle. Well, let's fix that. The next thing is it's not a specific force. Like push, pull, or friction. It's not, let's saying, it's not always friction. It's not always tension. It's not always the same thing. It's any force that's pulling us inside that circle. It's any force that's up, that's keeping us in that circular path. Any force that's present going in that direction, we're going to call centripetal force, because it represents the sum of all forces causing the object to move in a circle. That was pretty well stated, so let me write that one down. I'm going to say represents the sum of all forces causing an object to move in a circle. Okay, I'm gonna scroll my notes up just a touch, just a touch. Yes.
What does it say? Something the sum of forces?
Represents the sum of all forces causing an object.
Thank you.
Circle, no problem. I understand my handwriting's atrocious, but it's gotten me this far, sort of. Yes, represents the sum of all forces causing an object to move in a circle. So let's draw a circle. I've got shapes over here, and I can draw a circle. Let's make a, see, black circle works. And if we put it right here. Okay, so we've got a circle. And then if we just go back to our drawing tool, we say, well, there's our circle, and our object's going to go around that circle. Okay, and let's say the object is moving, let's go this way, clockwise. So the object is going around the circle, clockwise direction. And at this moment in time, let's just take a snapshot of it, and we find that it's sitting at the top. Okay, and then we want to draw the vectors for velocity, force, and acceleration. So if it's at the very top of the circle, or this would be if we're looking down on it, because it's a horizontal circle, we're looking down on it and it's at that 12 o'clock position. If we were to say at that moment in time, which direction is the velocity vector? Which direction would we say? What would it look like? Point with your fingers. Okay, from the ones that I can see, there's a lot of people not voting. So put your fingers up, point. All right, that was a little bit better. Anushka, point. There she goes. She sort of pointed, then went to a scratch. All right, so as it's going around, you can put your hands down. As it's going around, the velocity vector is actually going to be tangential to the circle, straight line. Okay, so this is velocity. I'm going to put a little t right here. So it's velocity v, and then I have a little subscript t for tangential. Okay, so the tangential velocity. You know this if you take anything on a lanyard like a string and you start twirling it, and let's say you let it, if you're twirling it even as a vertical circle, when it gets to the very top, if you let go of it, it's going to go straight across the room because it's actually moving tangential to the circle. What about the force? Which direction did we say the force would be going? Yes, so those that are voting, that's perfect. It's going down because remember the force is center seeking. Where's the middle of the circle? Middle of the circle is like right there. So the force is pointing down. Now, how well do you know your Newton's second law? Which way is the acceleration going?
To the
Say again. Somebody
the-
tell me out loud, which way is the acceleration going?
down or to the right, one of the two.
You're right. It's one of the two. Somebody tell me which one.
Down.
All right. Correct, because the direction of the net force should be the direction of the acceleration, right? The direction of the net force is the direction of the acceleration. So if the net force is down, the acceleration is also down towards the center. Now, if we come to since this is clockwise, let's talk about it like the face of a clock. If we went to what would be the 3 o'clock position, which I think is right here, our tangential velocity would be down. That's our tangential velocity. Our force would be inward. So we have our centripetal force, and our acceleration would also be inward, centripetal acceleration. We'll do one more just so you have the example. If you're at the very bottom, scroll this up a bit so we can get a little bit more room. Our tangential velocity would be going to the left. That's our tangential velocity. Upwards, we would have the centripetal force and the centripetal acceleration. No matter where you are in the circle, the velocity will be tangential, because if you were to cut or reduce or eliminate the force that's keeping it in that circle, let's say eliminate that force, like twirling a ball on a string, or for me, I have my keys on a lanyard. If you were to cut that string, cut that lanyard, that force no longer can exist because you've cut the string that the force is a part of. That object is going to go straight from you. It's not going to leave you and do an arc because there's no force pulling it in that circle anymore. And then the direction of the force is the direction of the acceleration. So that object is trying to go straight and is pulling it in. Someone asked, what do I mean by tangential? Tangential just meaning perpendicular to the forces, and it's going along the edge of that circle as a tangent. It's a tangent to the circle. If I was to draw the line out, maybe it looks something like this over here. Up on the right side, that line kind of comes through like this. This one comes through like that. Okay, so we've got the circle drawn. We know the directions of the velocity. We've drawn out the tangential velocity, or just velocity if you prefer. Centripetal force, centripetal acceleration. Let me see, I see some things come in the chat that I haven't been really watching at all. Can you please explain why, again, the acceleration goes in that direction? Yes, because remember Newton's second law. If we look at the net force, the direction of the net force is the direction of the acceleration. So acceleration follows net force. And if net force is inward, acceleration is inward. Let's see. I think I'm pretty caught up. If not, throw some more stuff in the chat. Now that we've got kind of an understanding of definition of terms a bit, we've got a drawing for reference, let's look at some formulas and see what we can put together. Okay. I'll do that on the right side. Let me change colors just so that way we've got some sort of contrast. I'll put them in black. That makes it look official. So centripetal acceleration, let me write that. Centripetal acceleration. been a year since I wrote centripetal, so I kind of slow down as I'm writing it. That is AC, and it is equal to VT squared, which is, you can drop the T if you don't like it. It's velocity squared, but it's the tangential velocity, but it's still the velocity squared. Okay, so I'm going to write it proper, but if when you're writing it, if that T just throws you off, it's okay to drop it as long as you understand that it's the velocity that's tangential to the circle. Okay, so we have tangential velocity squared over the radius. And then I'll just write down VT is tangential velocity and R is radius. So the center of the circle outward to the object, the radius. I'm going to scroll this up just a little bit. I'm going to make sure that the formula stays on the screen so that we can see it. Now, centripetal force. We have said that centripetal force is equal to mass times centripetal acceleration. But now that we have a definition for centripetal acceleration, we could plug in what we know centripetal acceleration is, so that depending on the variables that we have in a question, we could solve for it. So let's do that real quick. So we have FC is equal to mass times centripetal acceleration. Since centripetal acceleration is VT squared over R. So here we're just interchanging these two things. Let me use a little bit lighter color and I'll just mark them. So this and this are just interchangeable because up here I'm just showing that if you're given velocity and radius and mass, you could get your centripetal force. I got one more for you, just one more formula. I would say it's not too bad, but it's kind of one of those, it's in between. All right, let's write this one down. It's the speed of circular motion. Okay, the speed of circular motion, also known as the centripetal force, but let's title it speed of circular motion. That is VT is equal to 2 times pi. I use 3.14 for pi, but 2 times pi times R over T. Now, T is something that we've not done before. So let's talk about T for just a second. Okay. T is period, not like end of the sentence, but a period. So T is a period. Now, if you know what a period is, that's great. Just stick with me for a second. If you're not sure, you've been in a car, and many cars have tachometers. That is, like if you rev the engine, it shows how fast the engine's moving, usually shows it in RPMs, revolutions per minute, okay? Well, if you took a revolution, how many revolutions per minute you had, if you divided by 60, you would get revolutions per second, right? Because we're in the car, it's RPM, revolutions per minute. Well, if we divided by 60, we'd have revolutions every second, or revolutions per second. Well, that's how many times you can go around every second. Well, that's frequency. I don't want frequency, I want period. Frequency and period are inverses of each other, meaning if you have revolutions per second, do the inverse, 1 over what that number is, because period is seconds per revolution. How many seconds does it take to go one time around? Not how many times around you can go in a second, but how many seconds does it take to do one lap? So here, let me put T is period, which is seconds per revolution. Seconds per revolution. It's a new value for us. If we were to look at Earth going around the sun, we'd say, well, it takes 365 days. Well, there's 24 hours in a day. There's 60 minutes in an hour, 60 seconds in a minute. I hope I didn't miss anything in that. 365 days, 24 hours. Well, you can go straight to seconds, 3,600 seconds in an hour. But you could figure out the period of the Earth by how many seconds does it take to do one full lap. Now that we have that, that is our formulas. Those are all of our formulas. We could trade in any other one. We could do one other one. Let me add one more. Just let's derive one real quick. Let's say that we've got, let's see, right here, FC, we said is mass times velocity squared over r. Well, what if we don't have velocity, but we have the period and the radius? So let me draw a circle around this. We've got, here is velocity squared, and here's what velocity is right here, right? We could plug that in. This is one of those connections I want you to start to be able to make, is to say, well, I don't have everything I need, but I've got a combination of equations. Can I do something with it? You can absolutely do something with that. You can say, okay, well, I've got FC is equal to mass times velocity squared, which would be 2 squared is 4. Pi squared would be pi squared. And then I would have r squared over t squared. And then the formula is divided by r. So this r cancels out the square. So now I can come back in and I can take out the square, take out the r. And now I've got this derived formula right here by just further defining what velocity, tangential velocity is. So you see how we can take two formulas. We took 3 formulas and created, we took 2 and made one more, and then we took another one and made another one. So it really depends on the information given. You're going to use your guess method. Let me stop the share for a second. I can put it back up if we need to, but let me stop the share for a second. You're going to, when you're looking at these problems, you're going to list out in the margin or wherever, you're still going to use your guess method, just like we did back in kinematics. No, kinematics is not dead. Well, we're not going to use it today. We're going to use the guess method, what you perfected in kinematics, meaning you're going to write all of your given. You're going to find what it's looking for, put a question mark next to it. Then you're going to find a formula that you can use that has everything except for what you're looking for so that you can solve for that. Rearrange your equations and substitute numbers in and solve it. Let me take a look at the chat. Can you please explain why? Okay, I think I've caught up to that. Let's do this. Let's start the worksheet. I'm going to start number 1 and 2 with you just to get you warmed up. I'm going to keep you on the chat until 4 o'clock. Tell you what, minimum 4 o'clock. Don't leave before 4. So you've got enough time. Some of these are challenging. Some of these are easy. I'll get you started on the easy ones so that way you can work through the challenging ones. I'm going to stay on the chat all the way till 4:25. You have to stay till 4 o'clock. Okay, so let's look at just the first 2, get you started. And let's see, there. Okay, so this is our practice sheet. A child on a merry-go-round is moving with a velocity of, okay, so I'm going to write this in my margin. Let me get my drawing tool up. So I've got velocity equals 1.35 meters per second. When she is 1.2 meters, all right, so my radius equals 1.2 meters. She's 1.2 meters from the center of the merry-go-round. What is the centripetal acceleration? So I'm looking for centripetal acceleration equals question mark. I'll go back to my notes. I see that centripetal acceleration is equal to VT squared over R. So I would simply solve this by saying it's 1.35 squared over 1.2. Put that in a calculator and you're done. This is your method. For those that struggle, this is your method. You're writing your given in the margin, you're finding the equation that will work. Number 2, the moon's nearly circular orbit around the Earth has a radius of 384,000 kilometers. All right, well, kilometers. Well, we don't do measurements of length in kilometers. We do meters. So I need to convert that. Let's convert that. We've got radius equals 384 million. Because a kilometer is 1,000 of, or one, sorry, a Kilometer is 1,000 meters. So when I'm converting to meters, I've got to multiply by 1,000. Now the next part, it says in a period. Okay, so it's given us a period. So let me put t equals 27.3 days. Now I can't use that. So let's do a little conversion. 27.3 days. 1 day is 24 hours. 1 hour is 3,600 seconds. So now I can cross off days, I can cross off hours. Those all cancel out. Now I just need to be able to do the math and see what it is. So 27.3, get my calculator, 27.3 times 24 times 3,600 equals 2,358,720. That's the number of seconds. So 2,358,720 seconds. That's meters up there. Now we've got the period, we've got the radius. They want us to solve for the velocity and the centripetal acceleration. All the answers that they have on this sheet are accurate. I've checked through them all. My only variation is just a little bit. When I'm using pi, I use 3.14. They use more decimal places than I do, so my answer gets slightly off, but it's still a good answer. This should have at least gotten you started. I want you to work through this sheet, through the entire class.